Welcome to The Explainer. Today we're diving into this amazing paper that asks a really huge question. Could the smooth, continuous reality that we all experience actually be built from something discrete, kind of like pixels on a screen?
So let's just jump right into the big question at the heart of, well, everything. Is the very fabric of our universe a smooth, continuous canvas? Or is it more like a digital photo, where if you zoom in far enough, you'll find tiny, indivisible pixels?
You know, on one side of the coin, you've got the world of our best physical laws. It's a continuous world, smooth as a ramp, where everything flows perfectly, and we describe it all with the beautiful math of calculus. But on the other side, you have all these new theories, from quantum gravity to digital physics, that suggest deep down, reality is discrete, it's blocky, more like a staircase built out of fundamental little steps.
So right away, this sets up a massive problem, right? A paradox that has really had physicists scratching their heads for years. If the universe is fundamentally made of pixels, how in the world do the perfectly smooth, elegant laws we see in nature just appear?
I mean, think about it. The math that describes everything from a light wave traveling across the cosmos to the tiniest quantum field, it's all written in the language of the continuum. It just assumes you can zoom in forever and ever and never hit a bottom layer.
And this is the classic objection, the point critics always bring up. They say, look, a pixelated universe can only ever approximate our smooth laws. Yeah, it can get really, really close, but it can never be a perfect one-to-one match. It'll always be a little bit blocky.
So that's the real puzzle, isn't it? We have to get past this idea of it being just an approximation. The challenge is to find a precise, mathematical bridge that shows us exactly how a bunch of simple, discrete rules can somehow build the perfectly smooth laws we've actually measured.
Okay, so how do we even start to build that bridge? Well, this paper lays out a really clever and surprisingly simple toolkit for connecting these two worlds that seem like they should be totally incompatible. It boils down to just two steps, super elegant. First, you embed your discrete points. Think of it like putting little pins on a map. You're just placing your pixels onto a continuous line. Then, you do something called a pullback, where you go to that smooth map and you only read the values at the exact spots where you put your pins. So this embedding idea, it's simple, but it's really powerful. All it's doing is giving every single one of your little pixels a unique address, a specific spot in that smooth world. It's like putting little markers on a measuring tape, giving everything a precise location. And then comes the pullback. Once you have your points mapped out, you basically take a snapshot of that whole smooth landscape, but, and this is the key, you only look at the values right where your markers are. You're creating a list of numbers, a discrete sequence that perfectly matches up with specific points in the continuous world. All right, so we've got our tools, embedding and pullback. Now with these in hand, we can finally dig into the math and find something, well, kind of amazing, a hidden connection. And here it is. This is the big aha moment in the paper. It turns out that a super simple calculation in the pixel world, literally just looking at a point and its two neighbors, has the exact same structure as something from calculus called the second derivative, which is how the smooth world measures curvature. It's a perfect structural match. And you can see that structural match right here. On the left, in the discrete world, you've got this simple little formula using just 3 neighboring points. And on the right, the continuous world's tool for measuring curvature. The point is, these aren't just kind of similar. They are 2 different ways of saying the exact same thing. It's not an approximation, it's a deep, one-to-one correspondence. Okay, that's huge. We've built a mathematical bridge. But that still doesn't explain something really important. Why this one? Specific law. Why does the wave equation pop up everywhere in physics, from light to gravity? Why that one? The answer, according to the paper, is incredible. It's not that the wave equation is some kind of command handed down from on high. Nope. It emerges simply because it's stable. It's the rule that lasts. Think of it like this. If you could try out every possible simple rule for a pixelated universe, you'd find that almost all of them are just duds. Their patterns either blow up into total chaos or they just fizzle out into nothing. But a tiny, tiny fraction of rules are stable. They produce patterns that can last, that can travel across large distances predictably, kind of like, waves. And that's the punchline. Nature doesn't have to pick the wave equation.
Stability is like this massive filter. When you pour all the possible rules for a local, discrete universe through it, the wave equation is what comes out the other side. It's the only one left standing. It's not chosen, it's selected.
So when you put all of this together, it leads to a conclusion that is, honestly, kind of staggering. It really changes how we think about physical law itself.
And here it is, the paper's core thesis. Those beautiful, continuous equations we've cherished for centuries, they're not the fundamental laws of nature. They are effective descriptions. They are the large-scale patterns that emerge when a deeper, discrete system settles down and becomes stable.
So let's just walk through that logic one more time, because it's so powerful. You start by showing you can perfectly link a discrete world to a smooth one. Then, you realize this principle of stability acts like a brutal filter, throwing out almost every possible rule. What survives? What's the fixed point that remains? The wave equation. The law isn't fundamental. It emerges.
It not just leaves us with this incredible question to chew on. If a physical law, something we thought was bedrock reality, is actually just an emergent pattern, what else is? What other parts of our universe, maybe even space and time themselves, are not the fundamental truth, but are just beautiful illusions that emerge from a simpler, deeper, and maybe even pixelated reality?